Okay, so it's almost 3 p.m. already, so I'll get started with today's class. Welcome to this week 10 TA session on optimization methods for civil engineering. As before, which we did in the last week, I won't be having any slides as such in this week's content. It's mostly solving problems in our studio. So I'll be going through some of the examples that have been already been discussed in the uh, class by sir, and then we'll probably look at some of the related problems of assignment 10 that you may get, and maybe take one or two extra examples and I'll solve them. Before I begin with today's class, so I would like to ask you, Manohar, so do you have any doubts or did you face any issue with RStudio while doing assignments or running the codes last week? Okay. Mhm. Mhm. Okay, okay, great. So that's great. So I think then and this week also, I don't think there will be much of an issue in running codes as such, because I think I looked at the assignment. It was mostly of theoretical nature, so not much numericals and all were there. But anyway, let's get through those numericals. I'll share my screen and we'll get started. Okay, so let me share my screen. Yeah, hope my art studio is visible to you. Then I'll proceed. So I think sharing is done. So yeah, I think the art screen is visible. So I'll move forward. So the first problem that sir discussed in this week's lectures is the 1 plus 1 ES, which is the evolutionary strategy. So in 1 plus 1 ES, what we do, this first things first, this is not a population based algorithm. So you just have only one solution to begin with. So you define your starting point, so that must be given in this algorithm. And then what you do, you perform some sort of a mutation with a mutation strength, and you get to a new solution point. So that's the idea, and if you can repeat this across generations, 1,000 or something, you will finally get to a solution. So which may be better or may not be better in certain cases, whether you are taking the best of the two or whatever selection procedure that you are using. So in evolutionary strategies, so you just have a selection operator and a mutation operator. You don't have a crossover operator. So I think that have been discussed in the class, and also I think you might get one assignment question related to that. So let's get through this example. So first is you define this function. So for the sake of completeness, let me just comment everything. So the function is say x1 square plus x2 minus, it's written already, but let me write it down properly again. Yeah, plus x1 plus x2 square minus 7 whole square. And the domain of this function is given by the sequence operator, which is between -5 to +5, and this is for both these variables x1 and x2. And you have to minimize this function. So minimize the function, and the domain is defined already. So let me write the domain of the variables are defined. So within this domain, you have to minimize your function. Then you use this outer function, which kind of takes this x1 and x2 values, and it calculates this function values at say between this 5 and -5 and 5 for those two variables, and with an interval of say 0.1. So at all those points you get your function values, You may or may not write this keyword argument fun here, but nothing in this example that sir has given. He has written this already. And then you can do your contour plots, and these are your contour levels, and this is just the colors. So let's run this part. So for that, what you can do, you can take your cursor here and just get this running. So this is the first line, this is the second line, and next you will be running this contour plot, and you will get this contour plot. Okay, so I think this part was also been okay. Anyone joined, I guess? Yeah. Okay, so we have one more joining in. So I was discussing about this 1 plus 1 ES example. So let's move ahead. So first I have plotted this function with all those contour levels. Next is you have to define the parameters. So this sig is nothing but your mutation strength. I think sir has already discussed what is a mutation strength in the class. So if you keep it to a very high value, kind of like enlarge your search space, so you kind of jump from one point to another point which is very far off. And if you keep this to a very small value, then you kind of do some sort of a local search, so you'll be moving around at that locality itself. So that's the use of mutation strength. So first it is wise to probably do some sort of a global type search, and then you can do some sort of local search. Okay, do we have one more? Okay, great. Yeah, so let's move forward. Next, this one is the number of generations. This is nothing but your number of variables. I'll just comment it for the sake of completeness, and it will be easier for you to understand later as well. And this is your initial point. So let's run this part. So this is just assigning the parameter values and nothing else. And then what I'll be doing, I'll be plotting this initial point on this map or the plot itself. So this has been plotted by the blue marker. Hope this is visible. And next it's the main part, which is the 1 plus 1 ES algorithm part. So I'll come to this, but since now we have two more people joining in this week, so I'll just ask them, so whether you two faced any issues, Sandeep and Pooja, while doing the previous assignment in R. Are you able to install the packages or everything, or run the codes in itself? So can you just confirm? Then I'll move ahead with the today's class. Okay, great. And what about you, Sandeep? Okay. Yeah, probably he will reply later, so I'll move ahead anyway. Okay, so yeah, hope my art screen is visible again. So now you get to this 1 plus 1 ES algorithm part, where you will perform this for 1000 generations, and you will run this while loop for 1000 generations. So we kind of start with an initialization of 1. It's just like your iterations, number of iterations that you kind of perform, and you will later do this I equals to I plus 1 here. And this j is nothing but your variable. So be provided with the software and the examination. I'm not sure what you mean by providing the software, because it should be installed in your local computer, right? Otherwise I don't think you'll be able to run codes. So but still I will check with the main T of the codes, then I'll let you know probably in the next week's session. But it's better to have it installed in your local laptop or computer, whatever you are using, and try and see if you can run the example codes that have been provided in the class. And anyway, I think I was going through the assignment questions. Even if in some cases you just know the functionalities of R, I think you can answer most of the questions itself. So questions might be of that nature as well. Like you need to know what a function does, or maybe by which keyword you can plot. Those type of basic things you should know. So and if there is a heavy code that needs to be run, so I'll talk with him. Let's see what happens. Okay, I'll move forward with the class. So uh, first, this j is nothing but, again you need to vary this two variables. So this is a two variable function, so you can mutate along this two directions, two coordinates itself. So that's why you are kind of doing this j equals to 1, and if while j less than equals to this number of variables, you will repeat this exercise, and you will do this in every generation. So this is kind of a nested while loop that you have. So now first what you are doing is that you are just storing this function value at the initial point. Later it will get updated, but that's okay. First you can think this f0 as the initial function value, and then you are storing this initial point x0 to y, and then this is the key line, this line number 22, where you are performing mutation. So what you are doing, it's just you are taking this coordinate wise. So you have already stored this x0 to y and this yj. So when suppose j is 1, so you are varying that x1 coordinate, and you are taking the first value x0 j. Then what you are doing, you are generating one random number. So this 1 represents how many random numbers you are generating. This mean represent the mean of the normal distribution. So this is normal distribution you are using, and this is the standard deviation, which is sigma, which you have already initialized, which is the mutation strength itself. Then after doing this, you are just varied that one coordinate, and later you are just calculating the function value at that point. And if there is an improvement of your function value, so this is a minimization problem. So if your f1 is less than f0, then you are kind of updating it, your x0. So this y will get updated to x0 again, and then I'll plot this point, the updated point, in the plot itself here in the right side, and this is dot sleep is just for the visualization purpose. So now you can run this portion. So I have run till this point, you can see it from here. Then you can run this. So again I'll move my cursor here, and I have run this part I equals to 1. But when you will be running this while loop part, you cannot just move your cursor and press run, because that will just do one iteration of it. But you need to do it for 100 iterations, or 1000, sorry, your number of generations is 1000, so you need to do it for 1000 iterations. So what you have to do, you have to select this entire this while loop block, and you can press run, and it will perform your iterations. So it's being done. You can see this from here. You have moved to here, and let's see what happens after that. Yeah, so after that you have come to this point, and you have got the solution in the third quadrant. So you can print the solution, which is this x0. Yeah, so this is minus 3.78 and minus 2.8, and this function value f0, which is very close to 0 itself. So this was the sum of two squared terms. So ideally you should have a solution of function value of 0. You cannot do anything better than that. So, and also it again depends on the domain of the function, so that have been defined. Can you please rerun? Okay, yeah, I can run the entire part again. Yeah, so this part I can run it again. So what I can do, I'll just clear this plot, and let me run till this point again. Yeah, so after that I'll just run this while loop blocks. Yeah, I think there is some issue with the visualization. Okay, now you have come to here. Now it kind of stops. So I don't know why it's happening like that, but yeah, ultimately we're getting the solution here. So was that the issue with visualization, or like anything else you wanted to ask? Let me check. Do you have any doubts, Manohar, or can I just proceed? Uh, okay, okay, yeah, great. So then I'll move forward. So again, it depends on which I think in which quadrant you are getting the solution. It might happen that you hit here, or here, or here. So you can get different sort of solutions. It again largely depends on the number of generations probably you are using, or the initial point that you are using, or maybe the random numbers that you are generating. So those mutation strength and everything will play a role in this. So let me run it once more and see what happens. Okay, I think I need to clear that plot, otherwise I cannot run it again. Yeah, let me do the entire thing. Yeah, as you can notice, you have got a solution in a different quadrant itself. Your function value is again close to 0, and this solution point is actually 3 and 2, and you have got the solution as 2.997 and 2.003. Okay, so I think it's pretty simple to implement this 1 plus 1 ES code, because it's just picking one initial point, and just this entire block of code kind of remains the same. And in this class we are dealing with normal distributions only, so this will suffice. I don't think anything else will be asked from this. Okay, so let's this is very basic evolutionary strategy. The more interesting one is the mu plus lambda or lambda plus mu, whichever you call it, evolutionary strategy, where I can take the same function again and do a population based algorithm. I can run that, and then so in this method what you have seen, you can get to a local optima, because it is largely dependent on the initial solution that you have provided, or initial point that you have suggested, and you are just generating one solution out of it. It's not kind of a population based algorithm. But in mu plus lambda method, you kind of have some, suppose you generate some 20 solutions to begin with, and then by mutation you will generate again 20 solutions from all those 20 initial points. Then from those 40 points you can just pick the best 20 from that, and you can do it by different selection methods, and ultimately what you will be left with, you might hit different optima itself, and you might just find out the every optima that is here, or you might hit the global optima itself. So in this case all are kind of global optima and all are local as well. So let's run this code. So I think it's pretty similar. So the function value is similar. So the first line, let me first clear everything. So this button is for clearing the plots. This button is clearing the workspace objects. So I'll do that. And then if you want to clear this console, you can press Ctrl L. So that will get cleared as well. And now you can proceed. So suppose now you have this lambda plus mu s. So this first line, the function you can run this x1 x2, this is similar, so this is similar, the plot you will get will be similar, this defining of parameters are also similar. Here the only change, which is the population size. So let me write it down anyway. Then this is nothing but the lower bound of your variables. So this is lower bound of variables. The next one is the upper bound of the variables. So here, there are two variables here in this example. Now this pop this kind of, you do some sort of an operation here and you store it in this ini pop, so you're kind of generating this initial population. Now what it has been suggested, can anyone tell me what this run if function does? So what's the meaning of this line? Like, have you gone through this lectures yet, or should I like explain to you? Yeah, so I'm asking about this runif function. You can take a guess also. It's okay even if it's wrong. Or I can just go ahead and explain. Okay, did anyone unmute? Manohar, are you speaking something? Yeah, kind of related, but it does something more than that as well. So if you look at this, so you are kind of right that this is the population size. So you are kind of, suppose you have installed like this initialized everything to 20, then this min of lb1, what is it? So this is actually the lower bound of the x1 variable, and this max which is the ub1, it is the upper bound of the x1 variable. So here this is -5 and 5. So what it does, it generates say 20 random numbers, which is the population size, between that -5 to +5. So that's the role of this runif function, to generate random numbers, and these are the bounds of that random number, and this is the number of random numbers you require. And then what you have is for the x2 variable, so this is also similar. So here again you have this min lb2 and max equals to ub2. So this is taking the lower bound of x2 and upper bound of x2, and it kind of generates 20 random numbers between -5 and 5. So for the both coordinates, this is generating the random numbers. So this is like generating the initial solution points itself. So let's run this line and see what happens. Okay, I think I haven't run this LB and UB lines yet, so that's why that error came, and also this population size. So let's run those first. Okay, so this is fine, this is fine. UB I can run. Now you can run this line. Now what it tells you, so if you write this ini pop and enter here in the console, this essentially gives you 40 random variables between -5 to +5. You can see that no values are crossing that bounds itself, and this is just, first you kind of had 20 random variables for that x1, and for x2 you had 20 random variables. So the next line, what it does, it kind of stores everything in array. So it is taking this 20 as the row numbers, and these are your number of variables. So those are your two number of variables that you have, so that everything in the for the x1 values are listed in one column, and everything for the x2 values are listed in another column. So if you run this part, so let's see what ini pop is. So this is like arranged in proper order, right? So this is for x1 variables, these are your random numbers, and this is for your x2 variables, these are your 20 random numbers, and together everything is a solution or initial solution, the initial population that you have provided to your algorithm. So if you kind of plot it, you will get say 20 points scattered in this plot itself. So let's do that actually. So after this points function will give you those points. Yeah, so these are those 20 points scattered in this plot itself, and this is your initial population. So since this is a mu plus lambda ES algorithm, so you have this probably mu equals to 20. And the next line, line 19, what it does is that it takes this point, so this every solution kind of points, or every population that you have, this x1 and x2 variables, pass those as your argument to the function f, and it is calculating the function value itself at those points. So let's run this. So if you run f0 and you write in your console f0, you get the function values evaluated at those 20 points. And this cbind function, it kinds of binds the column. So this inipop has already two columns, one for x1, another for x2. The next thing that you are entering here is f0. So if you are kind of column binding it, it will the third column will appear here, and that column will correspond to the f0 values, which are these 20 values that you are seeing here. So let's run this again and see what inipop becomes. So this is your inipop. Yeah, now you have 3 columns, and this last column is for f0. Okay, so I hope this part is clear to everyone. So I'll move to the main part of this algorithm. So this is again what you do. You have already initialized your generation to 100 here in this case, and again you are kind of doing some sort of an iteration. So let's see and what it does, and just go through it one by one, line by lines. So first you can see that this while loop is for if your this I value is less than your iteration number or the generation number. This inipop has 3 columns, and if you're writing it as comma minus 3, that means you're just picking everything but the third column. So you're not picking the third column, you're just picking the first 2 columns, and you are storing it in new pop. So here if I write new pop is storing the first 2 columns of inipop. Okay, so let's run this. Just do one run line by line, and then I'll run the entire thing. It won't be a problem, I guess. Yeah, so if you enter new pop here, yeah, it has just excluded that third column itself. Next you do mutation, and that mutation has to be done to get to a new point, and for that what you are doing, you need to do it for all these 40 coordinate points. So you have 20 solution point, and for every solution point you have kind of 2 coordinates. So that's why it's like generating 2 times pop size, which is 20, those many random numbers, and you have this mean 0, and your standard deviation is the mutation strength itself. So if you run this line, let me run it from here. So if you now, oh sorry, if you now click on mutation, yeah, so these are kind of your random numbers that have been generated, and now what you will do, again you kind of do some sort of an array type storing, because you have this 40 numbers stored side by side, and this is for this pop size and n for that many dimensions. So if I run that and now run mutation again, yeah, this is now kind of arranged properly, that you can see. This is for every coordinate and every solution point. So after that what you can do, you have to add it, just add it, and you will get the new population. So your mutation will be done. So so you kind of update your new pop. So now new pop becomes something like this. So these are your new 20 sets of solution points. So you may again plot this on this plot itself, but that will complicate things, because since you have to run some sort of an iteration here, which I'll show you sometime later. But what you do, you just pick okay, I'll go to it. So first let's calculate the function values at this new population points. So this f0 will give you the function value, and if you do again this column bind kind of a thing, then you will get this as side by side, that's the third column. So after this, if you just click on or write new pop. Yeah, so these are your new function values at those new 20 points that you have got. This all pop does some sort of a row bind. So row bind is like you have 20 rows, and ini pop has the initial 20 rows of initial solution point. New pop has the 20 rows for corresponding to new 20 points. And if you do this, if you run this point, you will line, you will get all pop, which is nothing but will store all the information of the 40 points now you have. So the first 20 of from the initial solution points, and the next 20 is from the newly generated points. And you have your function values at every one of these points. So if you kind of can arrange this column, if not, and just pick the best one from that. So if you are kind of picking the lowest of 20 of those, you will get to your new solution set. So we'll do exactly that. So the first one is you need to convert it into a data frame in order to sort it in ascending order. So first I'll convert it in data frame. So once I do that, the main difference that you can notice is that here this column names were kind of this 1 comma in this square brackets, and this sorry, these were row names, and the column names were not properly named, just f0 were named. Now you have everything named, and you kind of have this indices, so it's not within the square brackets itself. So those indices go from 1 to 40, and this column v1 is for variable 1, this column v2 is for variable 2, and this column f0 is for the function value itself. So let's move ahead. Now what I'll do, I will order this in terms of this f0. So this $sign f0 tells you by which column you are actually ordering it, and when you write order, it will always kind of order it in the ascending order. So I think you can do the descending thing as well, but it will make things easier. So let's do that. So when I do this, now let's look at what all pop is. Yeah, so you can notice that these values are arranged properly. This is 15, 17, 22, 26, 34. It's all are in ascending order, goes up until 876. And you can notice that these indices are now different. It's not from 1 to 40, it has properly arranged. So earlier, which was the 28th index, corresponding to that row has come here, and so on. So that's why you need to convert it in the data frame. So I think this R does some initial checking with those indices and sort it according to this, probably this column f0. Okay, so now you store this 20 points. So this 1 colon pop size will pick the first 20. So this is 1 colon 20. So it will pick the first 20 of this all pop, and that will be your again initial population for the next iteration. And once I plot it in the contour map, what happens is that, before that, let's just go through this. So this ini pop is nothing but the first 20 points. It goes up until 88 now from 50. So this, if you plot all this in this contour map, okay, so I think everything vanished for some reason. Okay, so this is just the plot itself. Now I will plot the points. So this will plot your new points. So these are your new point, and you do I equals to I plus 1, and you kind of perform this iteration. This is again required for visualization and all. So I think you have understood the algorithm itself. So I have to run the entire thing, this while loop, but before that I have to clear everything and rerun, because otherwise there will be some issues. So I'll just do that pretty quickly. So let's run from here to here first. Okay, so this ini pop, so line 22 till line 22 I'll run first. You have your initial population. Now from this while loop, this entire while loop, you have to run this together itself. So this is for 100 generations. So let's run this. Yeah, so you can see that some points are in here and some in here. So this first, third and fourth quadrant had some certain points right now. Some points are moving out from the third quadrant, it seems. So it is still running. It will take, say, another minute or so to complete this. So does anyone have any doubts related to this? While I run this, you can ask. Okay, it has finished running. Let me check. Did anyone raise any hand or so? Nothing. Okay, so I think it is kind of clear to you. So you kind of get some bunched up solution here, here, and probably one solution you got here, and you got nothing here. That might happen in certain cases. Anyway, you're just interested with the global optima. So out of all this, the global one will be picked. So let's print this. So this is the best solution that you can get. So this is the best solution. So the function value is kind of minimum at this first quadrant itself. The actual solution we have seen using that 1 plus 1 ES was 3 and 2 for this point. So it is close to that, 2.97 and 2.03, but that's fine since we have not run this for many generations here. And the solution point value is 0.03. It is close to 0, but yeah, I think you need to run this for many generations, then only you can get to it. But since it takes so much time, so I'm not running it the entire thing. You can later you can change it to 1000 and see what happens in that case, and so on. So that's another topic I wanted to discuss. So there was one more example which is pretty similar. So just quickly go through this because then most of the things are pretty similar in this example. So this is again lambda plus mu ES that you will be doing. So first let me clear everything. Okay, so let's clear this. So here the function, it's kind of a different. So this is kind of you have a trigonometric function. Yeah, this 20 plus x1 square plus x2 square minus this 10 of cos 2 pi x1 plus cos 2 pi x2. And this function domain is same, minus 5 and 5. This is that. Then you can do the contour plot and you will get some sort of a plot like this. So you kind of have a lot of local minimas in this if you notice the contour levels and so on. So let's do this, quickly run this. So this is your mutation strength. Here I have defined it as 0.2 only. So let's do this. This number of generations is 100. I've taken number of variables is 2. Population size, I have used it different here. Earlier it was 20 in the example. Here I have put it as 400. Lower bounds are minus 5 and 5. Upper bounds are 5 and 5. So this is again clear. This part is again same. You are generating those random numbers using that runif function between those lower and upper bounds. Okay. What happened? I got some error, I guess. Just object UB. Okay, I think I didn't run this UB part. Okay, now it will be fine. Yeah, so after that you will kind of store it in the array. You can plot those points itself. So these are your 400 points that you have taken initially, and your function values you can calculate at that point. You can bind it using column bind, and this you can again store it I equals to 1, and this entire part remains the same, that lambda plus mu s algorithm. So I'll just run it quickly and see what kind of results you can get here. Yeah, so you can see that these points are kind of moving now. The visualization is kind of clear here, and it will run for 100 generations, I guess. It was 100 generations. That will take some time to finish. Okay, any doubts related to this so far, or anything related to assignment of this week or last week or anything? You can ask right now. Yeah, I think one. Yeah, Manohar has a question. Yeah, go ahead. Mm-hmm. Yes, yes, yes. So I think here, yeah, that's a valid question. So I think I have not written that part here yet, but I think when you do that, I think it was inside. So when you generate this contour plot here, I think the one command I'm not like familiar, or I cannot recall it. The one command that gives you the title of this plot, here you have to pass that generation number itself, and that generation number will be I here in every iteration. So in that case, that visualization will come here. That generation equals to will come, and I think it. Yes, yes. Another way you can identify is that this console, if you get some sort of an arrow sign here, yeah, this arrow sign appeared right now. It tells you it has finished. Otherwise, it is running. So that way you can also check. Okay. Hmm. Yeah. Assignment 10. Yeah, 10. I have opened it. You can, I think, probably view it as well. This one. Yeah. Is it? Which one of this is not correct? Okay. So I think it has one correct answer only, not two. It is asking you for the incorrect statement. So I think two of them are correct here. Yeah, yeah. So I think that's fine, I guess. No, it's all of the above means three of them are incorrect. That's not the case here, right? So all of the above goes out of the equation anyway. So you have now three options left. So out of this, I can notice that two of them are correct and only one is incorrect. That's okay. Yeah, yeah, no problem. Yeah. So anyone else has any doubt from assignment 10, you can ask. Otherwise, I'll go ahead with another example. Uh, so okay, so I'll probably move ahead. So yeah, so this is finished, and let's print the solution points itself. So this is pretty close to 0, and this function value is again pretty close to 0. So you can also verify this from this. I think cos 0 is 1, right? So this 20 and minus 20 kind of gets cancelled out, and this x1 and x2, if you put at 0, so you get a function value of 0. So that's the optimal solution here, and you kind of got it very close to the optimal one. But it might happen that you need to do some more iterations on top of it using the gradient based algorithm. So what you already did in the classical optimization part of this course. So in the next example, we'll do exactly like that. So this is a hybrid method that sir has talked about in the class. So this is the particle swarm optimization method. So it's a pretty simple method. It's just one line of code and you can get the answer. So I'll discuss this. So let's clear everything. So yeah, for this, as you installed your genetic algorithm package, GA package, in the last week's class, you need to do something like that again. So you have to have this install.packages and this PSO for particle swarm optimization, and you need to have an internet connection to install this. So since I have already installed here, I won't be installing it further. So let's do this. I'll do this first line, library PSO. It kind of imports the library here in this environment. So let's do that. You can also check from this packages itself. So if you go down, or you can see that probably somewhere. Yeah, so this PSO package, particle swarm optimization, the version you can check. and this tick mark means you have successfully imported it in the environment. So you can now proceed to use your PSO package here in R. So let's do that. So again, you can have these two functions. So first, let's do the simpler one. So this is the same function that I have talked about in this class. So here also the optimal solution was somewhere, I think around 0 or something, 2 and 3 or something like that. I know we noticed, or probably it was 3 and 2. So let's run this again. This is again your sequence function. This Z, this contours, this contour plot is done, right? And then, yeah, so this is the critical stage. Now last week we also talked about you can write your functions in different ways. One way of doing it is like passing arguments x1 and x2 and write it in this fashion: x1 square plus x2 minus 11 and so on. Another way is the vectorized form, which is you pass this variable only x and you take this coordinates, say x1 or the array, whichever you call it, the first element of the array, and square it. So this will kind of represent your x1 square, this represents your x2 and so on. So if you write it in this vectorized form, then there is an advantage of you can just pass it in this PS optim, which is the function for this PSO algorithm. There if you initialize everything in this vectorized form, like the x1 and x2 variable you have, you kind of say that I don't do any initialization. You can pick the default initialization and do this particle swarm optimization. So I think this particle swarm optimization theory has been discussed in the class, where so to talk about it briefly, you have one point, suppose a solution point. From that you move to another solution point depending on your own, say, direction, and then your best solutions direction. So you kind of move towards your some sort of movement towards your best solutions uh, like direction. So this is kind of local thing. Does anyone have any question? Yeah, Manohar, go ahead. Yeah. Yeah, sure. Which lines? Yeah, sure. Yes, correct. Yes, that's true. No, no, you need not do that again. So you can just use this itself. Yeah. That's a good point. Actually, I think Sir did this extra, so you need not do this. Yes. Yeah. So yeah, so I think particle swarm optimization tells you to move somewhat in your like current direction and then your best solutions direction, which is a local search, and every solution point kind of can communicate with each other. So you can kind of can move to the global best solution, so that direction itself. So those have some sort of an this CP and CG coefficients involved in that. So this one is for the movement along your local best direction. This is for the global best direction. So these coefficients you can set it up. And as I have mentioned, if you are passing this as vectorized format, this f has to be in vectorized format. So if you don't run this line again and you pass this f, then you will receive some errors. So let's see if that's exactly the case. So after this contour line, suppose I am running this line directly. The seed thing, I'll get to it, but it's not that important. Yeah, you will get this error in this function. So argument x2 is missing with no default. So it kinds of thinks that you are passing everything as vector and you don't have that argument x2. But actually, what if you do this line first? If you run this line and now you do this, I'll run this. But first, let's get through this parameter. So this is if you write instead of na, if you write here as 2, that means you are setting your initial point to 2 and 2. If you are writing here as 3, then you are setting your initial point to 3 and 3. This 2 is for the number of variables that you have, and this 3 is for the initialization of 2 variables. If you write here as na, you don't initialize anything for those 2 variables. This is f, this is the lower and upper bound of those 2 variables. This control list, it tells you the absolute tolerance value that you are giving. So this 1 e to the power minus 8 kind of gives you the tolerance level. The C1 and C2, or CP and CG. So in the slides, I think it was around C1 and C2, something like that was written. So this sum should be close to 4 or something. You can set it as different as well, say 0.5 and say 3.5 as well. And this hybrid of, if it is off, then you are not doing any classical optimization, gradient based search after this. You are just getting the PSO solution itself. I'll get to it if you do it, if you write it as on, what happens in that case. So let's run this line. So now you can run this line, and I think I didn't plot anything here, but yeah, in the next line I'll plot that. So this is the solution that you have got, and if you print this, the solution value is very close, like 2.99 and 2.00. So this is kind of 3 and 2. So let's run the other function that gives a better visualization of this hybrid thing. So let me comment this line and this. So now what you can do first, I have already installed this package. Okay, so let me run this entire thing first. Yeah, so you have this plot. Now you will just run this. Yeah, so your run is complete. You will plot the point and you will get the function. Yeah, so you can notice that your solution was 0 and 0, and you got something like 10 to the power minus 5 and 10 to the power minus 9 here, of that order. So that's okay. So let's do this. Suppose I just set it as 2 and 2 and see what happens in that case. So let's run this part again. Yeah, you kind of got the same point again. It's 10 to the power minus 6 and 10 to the power minus 6 in that range. Let's do hybrid on here. So after finding this, okay, is there any? Yeah, make hybrid on. Correct. Yeah, so if I do this, or did you ask any question? Yeah, if I do this hybrid on thing, what happens is that, yeah, I will get in terms of say 10 to the power minus 10 and 10 to the power minus 10 in that order. So it kinds of improves your solution and moves closer to 0. So that's the thing, you can notice the difference in those cases. And you can pick this CP and CG as per your wish and check how the solution varies. And also this absolute tolerance, you can change that and can also check. And initialization should not matter much, but you can check that as well. And I think that's all about particle swarm optimization. Let's quickly discuss, I think 1 or 2 assignment question I think was there related to R, so we can discuss that. But before that, let me ask any more doubts related to this, or any assignment or anything. Yeah. So yes, you can write equal to as well. So let's try that. Suppose you write, yeah, go ahead. Yeah. Were you asking something? Suppose, yeah, write this. I didn't find much of a difference in here, but I think the key difference is here that what I feel is that if you write x1 equals to x1 plus 1, then there could be an issue in that case. But if you write x1 equals to x1, like if you do this kind of an initialization, that might be a case. So you're kind of updating it, this x1 here. And I think this is not a valid equation that you have written, because x1 can never be x1 plus 1, right? So let's try this. Since you raised this point, suppose I initialize everything to x1 equals to 5. Okay, so let's run this line quickly. Yeah, so your x1 is 5 here. You can see this from your values. If you update it, the line 20 to 1, first do this, let's do this, then it gets to 6. Now again, say I initialize it to 5 again. Suppose I do this, I don't know what will happen, but my guess is something wrong might happen. This here also, oh, it worked, right? Okay, so I think both of them, then it's fine, I guess. Both of them works. Yeah. So this, yeah. So yeah, even I have a doubt here. Like I'm not that familiar with R, but in Python also you can write this x1 equals to x1 plus 1. This arrow sign seems to be some sort of a functionality of R itself. Like you can write both of them, so it doesn't matter. You can write either of them. That's the thing, I guess. But if anyone knows anything more about this R, then or maybe I can search on the web and let you know in the next class or something. But I didn't find any difference between these two. So, okay, so let's just quickly, some 5 minutes are left, just quickly discuss, I think, couple of assignment questions. I think you will get a pretty simple question of one plot, so let's clear this. Yeah, so this it asks you how many blue points you can see, so you don't even need art to solve this problem. If it's 0:6, that means it takes a step of 1, and that 0.6 is included, so it's 0 1 2 3 4 5 6. That will be 7 points, so you don't even need to plot or count it or anything. But yeah, it's pretty simple. Next is another question. I think this function value is kind of defined in a vectorized format. Then if you do this x1, this c4 comma 4, then your x1 becomes this point 4 comma 4, and then you can pass this point to your function, and that will be your f1, suppose. And if you write this f1, it will print out your f1 value. So I think here it's 250. So you will get something similar as well. Okay, so another one, let me quickly run this 1 plus 1 ES algorithm. So the function here, it's different now. This first part is kind of similar to the example that we have seen in the class. The second part I have modified it a bit, like minus 10 times this 4 of cos pi 1x1. This here you have some 8 multiplied here, and the rest of the things are kind of similar with the plots and contour levels and all, and also the initial points and everything you can set it up, and the entire code is similar. So let's run this and see what happens in this case. Let's run this part first. So this is the plot you have here, and now your starting point is somewhere here. And if you run this 1 plus 1 ES algorithm, so if you can run this entire thing together and see what happens. So again, I think it's running. Yeah, since you didn't get the arrow sign here, it's running, and your run is finished. And finally, so you got all these points, and let's see which one of those were the best ones. So the best one was around very close to 0 and 0, and your function value is very close to minus 30. Another example could be on PSO itself. So you can again import this PSO library. I think I have already imported it, but that's fine. And this PSO optim function, so you can write it in this fashion as well. So I think it's pretty similar to what we have seen here as well, but I'm not giving any control parameters as such, so it will just pick the default ones. and let's see how this sort of a solution looks like. So I haven't plotted this for this, but for this function, the value, like optimal value, will be around minus 40, 0.45 or minus 0.18, and the optimal solution will be 9.90. So you can just play around with the functions, and you can also plot it and see what happens and so on. So it's almost 4. Let me check if anyone have any questions related to the material that we have covered today. uh, if not, I'll stop today. So anyone have any doubt, you can join the other session. I think that will start from 4. So yeah, you can do that. Next week, I think there will be some discussion on MATLAB software. So introduction to MATLAB, and all some of the optimization problems will be solved using that. So you can again, I think the lectures are not yet posted, but once it is posted, you can try it out and see if you can install it in your laptop or computer and run the codes that have been given. Okay. So any more doubts or anything? Okay, so yeah, you can join the session which is from 4 p.m. So